Okay, so I will start by again introducing
Hmm.
the problem setup, you know. So technically we were looking at a problem where we are trying to learn the operator, right? So we have been exposed to learn about the Euclidean space, and now I'm saying this because in a moment I'll be actually introducing the concept of discretization and discretization invariance. So that's the reason today I started from the point of Euclidean space.
Okay.
So far we have just seen any sort of neural nets, be it MLP, CNNs, RNNs, transformers. They are mostly confined to Euclidean space, right? And now that we are kind of are you getting the noise that is
No. You said they're only confined to Euclidean space. I was going to say they're not confined to Euclidean space. They're confined to discrete spaces, yes, but they're
that's
not
still an
confined to you.
so here is the deal. Discrete spaces, whatever has been considered, they are kind of been treated as Euclidean space. They are discrete, certainly they are discrete. So discrete and Euclidean are not same in this context. By Euclidean I meant that the norm. So here is the deal. Euclidean, there is this thing that is kind of being maintained. You can see, right? I can write and you can see.
Yes.
Technically, it is this kind of thing that is being uh, the distance is being maintained by this. If you remember the video that I was showing last time, so again we will get to the Banach space. In Banach space is the generalization of all function spaces. In very simple terms, I don't want to dive get into the exact mathematical definitions, but let's say this is Euclidean. And if you remember that circle and that square analogy that they had given, that circle becomes a square in terms of distance. So technically in Euclidean, if there is this point x, y in this case,
Hmm.
or let's make it like this for ease, or even easier. Let's use this. Here is x1, y1, x2, y2. In terms of Euclidean distance, should be what? X1 minus x2.
So in your iPad, can you on your top right make sure it is clicked follow my view?
What is that?
Basically, right now it forces me to follow the purple Tiasha Sarkar, which is your presentation screen. I have to manually follow you with the blue one. Blue is your iPad wala zoom. So in iPad zoom, do you see an option on the top right in your whiteboard where you can say follow my view
Oh no.
in your iPad zoom?
Can you see things now?
Yes, perfect. Yes, thank you. Thank you so much. Yes.
Excellent. So, oops. Let's make this little here. Is it still? So this is the whole of the. This is the gist of, and this is how I want to call it to be Euclidean. And what happens to
Hmm.
Banach space? Technically, you are going to abstraction level up. Technically, right? You are going to another huge spaces where the distance is being different, like defined by some way, and also, and in this case, in Banach spaces, you are not limited by this kind of vectors. There can be many vectors, there can be sequence of vectors, and there can be more vectors. It can be even a function. You are kind of that will actually lead you to keep this picture in mind, because I'm about to explain you the discretization invariance. So this is the kind of motivation I want to give at the beginning. So this will actually lead me to introduce the concept of discretization invariance, which I'm going to explain soon. But all I'm trying to say is that So if you hit out from Euclidean space to, like, if you go to abstractions level up, in this case, the orange circle, the higher space. So from the points, you're getting vectors and then sequence of this kind of vectors. And even if you think of a continuum space, it will become a function. And technically in Banach spaces, no, pause me. If something you cannot follow, just pause me. But
The continuum part I didn't understand.
Continuum, okay, continuum in this case is
non-differentiable at any point?
No.
No, sorry, differentiable at every point. Sorry.
It's a continuous function altogether.
Oh, so a continuous function. So the only way to be able to define that is that it will be continuous at every point, right?
Yeah.
Sorry, it will be differentiable at every point, right?
Don't bring. I mean, yes. I will say yes. To be honest, yes.
Okay.
Yeah.
Okay.
Okay.
All right.
Differentiable at every point, and
how else will it be a continuous function? Otherwise, that's what I'm thinking.
No. Continuum. Yeah. Theoretically, all I'm trying to say that we are actually. So now discrete. Now Euclidean, I define in terms of norm, right? So you see that I took some discrete points and defined a distance, which is in this case, sometimes we call it norm, like this in math. You probably have seen this. Oops. Again, what? This you have seen, right? This kind of notation.
Dot operator?
Not dot operator. Basically, this kind of thing, this D essentially. The distance, the norm. For example, you have seen a vector divided by this
its magnitude.
Magnitude. So the distance magnitude, I'm trying to
so that is the norm. So norm is just a short term for normal vector, which means if we take the direction and multiply it by the unit vector of whatever that space is, that is the norm of that vector. Or
it's a unit length vector technically. Unit
if we take, or the other definition, just because you know me, I'll take same things to explain 5 ways, which is if I multiply the.
Hold on, I made a mistake. You should have caught this. Anyway, this is the unit vector. I'm sorry, I made a mistake, and this is okay. This is just the magnitude of A, right? Yeah, I will also bring equations which I have not seen. I mean, this is very basic, but yeah, I mean, so sometimes norm, distance, these are all the kind of colloquial terms used based on the literature, the kind of literature you get to see. But my goal is, what I'm trying to say is, you start with the Euclidean space, whatever we leave, in deep learning, generally you follow the Euclidean space. And by Euclidean, you can think exactly how in normal geometry, the difference measures are being maintained, like the triangle property and everything, right? And that's the geometry that is being internally maintained by the spaces that your neural nets, where your MLP, CNNs, or your transformers are being used. That's why there is a sentence which says that, and I have actually highlighted this because this is the crucial part. But the paper claims that they have deviated. So they say that in page, in page two, they say that, for example, families of graph neural nets and transformer models are resolution invariant. See, in our approach, somewhere in page 2, they have said, but they fail to converge to a continuum operator as discretization is refined. This is a very crucial sentence that is a motivation of pursuing the neural operator literature.
Really? If discretization is refined, you're telling me that they will never become a continuum operator?
This fails in transformers or in any sort of neural network, be it CNN, be it graph neural network, though I have never used graph neural network, but that's the claim that these people have made, that now now that we have a framework, we can make it refined. If the more refined, so if you see figure 1, now go back to the paper and see figure 1. You see that there is this a kind of white grids for the mesh, and they get refined. The more refinement, the more discrete samples you take, the more continuous it becomes. For example, let's say I want to estimate a function, okay? You take white space, and they have actually kind of, that's why this paper is hard, because now you take finer samples, right? You take even fine samples. You're kind of approximating to the continuous space. These two
limit tends to infinity is where it will become continuous.
Exactly. See, I'm trying to develop your intuition, because you will exactly see this limiting condition somewhere in discrete invariance, right? So okay, and then essentially let me bring us back to the problem setup that we saw last time. Is let's see. So we are actually, so these are the equations that might look a little familiar to you now, because we said that we are kind of having two spaces, two Banach spaces. What happened? A to you, right? This you remember. These were the Banach spaces. And Banach spaces, for now, you think of like generalization of all functional spaces. And we were having this operator, which is mapping one function space. So far in neural nets, essentially, you are actually having Euclidean kind of input, Euclidean output. And then over here for neural operator, technically you have a function, in this case A's, and you'll have another function as output that is, let's say U's, right? That's what. And this, so this is currently, we are actually, this is also an operator. This is the operator essentially G.
Okay. Just for refinement again.
Yeah.
Okay.
Yeah.
G
plus.
G is the operator that you're calling neural operator, which maps between capital A and, so this is my problem. So this is capital A a set?
Function space.
Okay.
And this kind of function space is denoted by this Banach spaces. Does this picture from last time is clear to you?
No. Yeah, this makes sense. The Venn diagram makes sense. This jump that you just made, right? Like this arrow that you just made, that is not intuitively clear to me yet. But I understand that it can be if I dig. Like just like Euclidean space has some rules, Banach spaces will have some other rules, right? So
more generalized rules. You can. I mean,
yeah.
I was just looking at the. So I can even make the picture of Euclidean map to Banach spaces, since I spoke about the distance and the norms and the and everything. So in Banach spaces, if you have, just imagine now these x1, y1, x2, y2, which I showed just now. These are just a point in Euclidean space, but imagine now this could be a function. Imagine it could be some function which has variables like x variables. It could be zillion number. It can vary from one variable to zillion variables. Okay. And if you really want to measure a distance between that function, you will be able to define that distance in Banach spaces. And what you can extra do is, if you really want to find some sort of convergence between those functions, the point of convergence will also lie in that entire space. So that's
Yes, yes.
they actually
That part
check
I
it.
understand.
Yeah, that
That part.
they call it Cauchy convergence rule. I think that will eventually fall in that Banach spaces. The convergence point will also fall in the Banach spaces, and that becomes the formal definition of the Banach spaces, if that makes sense, right?
Okay. Okay. So, but
Okay.
again, even though I can't represent this correctly in my head directly, like A is to U, for example, if this is the definition of Banach space, then you're telling me that at
A
least it
is to you,
maps
nahi. A
from.
is to you, nahi. Sorry. Don't think it to be a ratio. Don't think to be it to be a ratio. But for now, imagine that a space is being a functional space A. I just wrote Banach spaces just to maintain. This was my intention that both A's and U's are Banach spaces. It's not this. Forget about this. I'll erase this if that confuses you. But or let's where is the until part? I'll erase this. This is much better now. You have a
Okay.
function space A, you have a function space U, and there is a reason why I made a small u, because you remember, right? We were having a discussion that elements in space A, elements in space U, right? That's why
Yeah.
it
So
is represented by small a's.
small a.
Yeah, but the whole goal is your input is a function space, your output is a function space, and you're learning an operator, which is G plus in our case. But now we are trying to estimate. So now with this learning learning mechanism, we are trying to estimate another operator which should be closer to this. And the way we estimate is by bringing in some parameters theta, right? And that's why last time we were calculating we were actually doing this kind of error. To see how much the mapping is closer to the original. And that has taken us through equation number 3, 4, 5, if you remember. This was the problem setup essentially.
Yeah. We
right?
were in equation number 3 is
I
you have
ended
drawn
up
up
at
equation number
equation
3.
number 5. Yeah, this is actually equation number 3, right? G dagger, G theta. So technically G dagger is something, let me see. In particular, this G dagger was measurable. See, they said it already. And what I think
And G dagger is the space we are approximating as and this is the neural network side. That means G dagger is the right imaginary right answer, and then that is what will be probably trained around it, right?
because theta is the parameters we are training it. See, in equation 4, they are minimizing the theta, right? So
They're
your
minimizing.
model will actually learn this one. Your neural operator model will learn this one, this thetas, because we were actually,
Okay.
right?
I thought it was G dagger. How do
Yes,
you? But it's
you are,
no. It's an
no.
absolute and then a difference. It doesn't matter. But that's what I'm saying. If you're minimizing theta, then G theta is our prediction. So तुम G theta minus G dagger लिखो या G theta minus. So I don't know how that works, because the way we are working on where sign does not matter, we can just do like, okay, this is how learning works, which is
I think last week when we met, I probably say it in the other way, because today when I was reading, I have got a little more sense because I just progressed a little bit, because
okay.
thetas are the measurable thing that your model is going to learn. So if I'm
Got it.
sorry if I have presented this in the opposite way, but the truth is actually G dagger is the original function that could have existed, but we do not know. So we are having that to be estimated by our neural operator model by bringing in thetas. And these thetas, you will see how they turn out to be the kernels and every operation that a neural operator is going to be made up of.
Okay, fine. So yeah, this is regular learning. This is how we did.
This is still, so this neural operator still follows the supervised learning itself. There is no huge difference, honestly. It is still a
Yeah.
supervised learning. It is still a data-driven model. You don't get the function spaces in general. How much ever Camier states about the heat equation, Burger's equation, Darcy flows, Poisson's equation, whatever, you are given the data set in the real world. No matter what your AIs and UIs are all, your UIs are all real data set. You are still following
I want to find out where their data set is, but okay.
Because yeah, I mean, I have played, so the way I jumped from North was just looking at the Darcy flow and then having something out of my just mimicking my Nerf to North. But that was a like disaster. It just failed, just like that things will fail. You just go ahead and but essentially this is how it works. Like, you are actually learning an operator. That's the whole goal. Now you see, you're learning operator from the numbers. So what happens? Let's say before neural operator, how these problems used to be solved. You need to have some this kind of things, numerical methods. Are you aware? So you can Google numerical methods.
No, numerical methods are mostly analysis. It's like numerical. You're discrete. You're
Yeah, we have
discretizing for
done
the sake
numerical
of
analysis
discretizing.
in undergrad. Yeah.
Ah.
So these kind of problems used to be solved with numerical analysis. This partial differential equations. If you remember,
Yeah.
there used to be partial differential
So
equations.
a simple question, right? How does a calculator calculate the value of pi? Numerical analysis only, no?
That's the thing, right? So here is the deal. So these things were actually learned by numerical. So these partial differential equations. That's why I said that you can do the integral. No matter what, you can do the integral with the neural operator. That's the debate we were having on Wednesday, and it took us to AGI and everything. But no matter what, now you are learning this operator. You are still following the supervised. So how they have made it complex, but
AGI.
intuition is still the same. You're still in the supervised learning setup. Right.
Because I can see when I see the square term, and then I see now I understand G dagger G theta so well. When I see that square term, it immediately opens my hand as this is supervised regression.
That's the thing. That's why I said that you don't need to even be worried with the partial differential equation. You can do hell out of this. It's just what addition they have done, it's the refinement of the grid space. That means you can make,
which is good.
Super resolution.
Great, they've done good work.
No, super resolution. It basically solves that super resolution problem. And when we do 3D reconstruction, that kind of zoom
so you can actually make this pretty nice. You can if we find a way to connect this to Nerf, this will be like super cool.
It's easier said. That's the thing.
In 2 chapters, I understand this G dagger minus G theta so much better now, because the previous one was EAU estimates, and I did not understand that notation.
Yeah, but now about EAU estimates, but forget about that. Expectation, it's you have to average. As I said, expectation, you have to average things out, and this summation equals to 1 by n. Let's say there are n samples, you have to do this average no matter what. Forget about expectation. I went through all the equations. That was my goal, but not to confuse you.
Okay.
But this is the takeaway. G dagger minus G theta that you are estimating by this parameter theta. It can be theta 1, theta 2, how. So we will see how many kernels they have done. 4 kind of kernels like graph, Fourier, whatever operators. But here is that's why I went to again on this equation. And I knew this time you will understand the expectation, and I know I just went over every equation last time.
Thank you.
But this is my saying is like it still follows the supervised learning setup. Now we have functional space.
There's a colloquial term in machine learning which is called there is no free lunch. Basically means, you remember how I was getting excited that wait, we have an operator that maps from any function to any function. I was like, I have AGI with me. Well, yes, I have AGI with me. You know what? This can lead to AGI only and only if I have the data set of AGI beforehand.
So here is the trinity of machine learning, and I'll write this. I do not know who is gonna watch, or Flip is gonna watch, because Flip would be happy, and I'm gonna put it on our general Slack channel. I do not know if David is gonna watch, but Okay, trinity of machine learning, and we really need this in order to make any ML algorithm work.
Universal function. I want to see what your
I have
unbreakable
recently
triangle is.
I have recently found a neural net, and I have to dig into it. I do not know if it exists any code repo. So there is a net called Liquid Net, which is inspired by a worm, which has just 309
Liquid
neurons.
net. Liquid. By the way, liquid net. Yes, sure. Neuromorphic engines you are going towards, but
I
uh,
have never used them. So listen. So it
huh.
is being inspired by some tiny microorganism which has 309 neurons. So that's why you can get rid of 10,000 or 1,000 and millionaires, millions of neurons, and can just have very few neurons in it. And still, so I figured this out because Daniela is coming here, and then her team, it came out from her team. So anyway, I'll not get into that, but yeah, the Trinity is this. Um, you were curious what I'm gonna write. Um, let's see. Data. Your AGI will be there. Algorithm and infrastructure.
Yes, I thought you were going to do an impossible trinity. Like you can only choose two, not the third one. So that I would understand. But yes, this is
You,
right. This is correct.
right. You have a AGI. You now also have an AGI.
Mm. Yes.
Flip will say,
Technically,
Flip will think that it's like these guys are debating since Wednesday.
no. But yes, right. My
You
original
still
intuition
now
was right.
have
Neural
AGI.
operator.
You can make transformer AGI. You can make LLM AGI. You can make heck.
I need to have the data set of the AGI first, no? So chicken and egg problem, no? So no freelance
This
theorem back again.
and having this data is like you said how many billion 13 billion people in that world in the world, and what
Yes,
model you meant.
currently, but that's not how much information they generate. They
Yeah,
generate
exactly.
way
So
more information.
you followed a compounded rule. I followed a simple, and that was Lip's term. Like anyway, whatever. But algorithms, we think and we make it efficient. That's good. Infrastructure is something that it's still being improved. This is a huge challenge.
So reinforcement learning and all of that is where I would have thought this would be all going. But then again, I didn't know how neural operators were working. I thought this was something else. Apologies. I'm still interested because it is basically giving me godlike powers of what the next neural network should look like, which are things like this. So
Yeah,
let's
I
go.
mean the beauty is the why this is important, because we are governed by the world. Let's make picture, because I am supposed to. I have given a challenge just to draw and not to write.
So essentially, also you can represent all Euclidean problems in Banach space problems anyway. So this should technically apply
That's
to.
the beauty of fun. And I remember why I said measurement theory, because the other day you came and said, "Hey, I told you to have like what measurement theory?" Yes, because these definitions, one time Borel measure, one time Lebesgue measure, these all comes from measurement theory. Even I'm also not introduced to this. Functional analysis deals with going from one space to the another spaces. They have made
Hmm.
it
Oh, wait,
critically.
functional analysis teaches you how to go from one space to another space.
No, not from Fourier space to time space. Again, don't get confused. These are, again, that's a frequency domain kind of thing. But I have never taken these courses, but it is just coming up from this paper is like crazily, they have made it unnecessarily,
Since you like books.
crazily mathematically involved for
Hmm.
for reasons, because this world model that I'm drawing is obeyed by physical laws.
Hmm.
And how many thermodynamics, whatever other equations I'm not able to think of. So in Camille, in the ICML talk that Camille was giving, the 2 hour talk that you sent me, so
Hmm.
he measured, he showed how many branches are that exists, starting from neuroscience, agriculture, I mean all sorts of engineering, everything in the world follows the physical laws, which there are integrals, different. That's why PDEs is not important. That was my claim, that even if there is an integral, it should work.
Hmm.
But they claim
Okay.
that mostly the world is governed by partial differential equations, and that's why they had to move from Euclidean space to Banach spaces, and that's the reason of learning an operator instead of just a model going from just
Interesting.
discrete set of data to discrete set of data.
This is super cool. Then yes, this would be what would be, I would say, the more generalized form of neural networks. This is such a cool paper. Then this is a way. Okay, I
Do
had
you
lost my
think, do you think
interest from
for
AGI.
unnecessary reason this paper is cited like 1,500 times now, and depending upon the
1,500
time that
times.
1,500 times, yeah. You just check the citations.
But then again, it's NVIDIA's NeurIPS papers. At this point, if NVIDIA writes that I have AGI since yesterday, people will cite it 5,000 times. So I'm sorry. It just currently NeurIPS situation, ICLR, all of those places situation. You can see who the sponsors are. You can see who the boards are, and you can also see who the authors are. Nice, very giving yourself medal kind of meme. I will give it here. However, NVIDIA, like again, the people who are doing this are doing in there are two ways. Like I said, no, you can change the ensemble or the model itself, which is your, let's say, neuromorphic engines, and you can go from there. Transformers are more, I would say, a little bit of
No
an
idea on
ensemble upgrade.
neuromorphic engines, by the way. I don't have any idea on neuromorphic engines.
Modeling it, not neuromorphic engines, but basically take your neuron, mathematically model it, and go like, okay, how does that work? That will look like an electrical circuit where a signal or a stimulus is going to your neuron, filling up like a well, or filling up like, imagine like it's filling up in liquid or something, and then it bursts, and then other neurons are activated.
Okay.
It
Okay.
like think
I have
water
to try.
channel kind of. Yes, it's irritating, but it is a, I would say that okay, because it is mathematically modeled based on what a real neuron does, it will
So
probably be.
technically, in my understanding, look, in these are all some models that I did it in my undergrad. So there are these concepts of control engineering that I did, controls, where we had this kind of forward model and a feedback loop. Right. This is
Feed forward system.
Technically, this is where the later on new reinforcement learning came in to the picture. Okay. Forward loop, feedback loop. Technically, this is how this controls took us to reinforcement learning, right?
Okay.
Now imagine that this kind of feedback could be generalized. I'm just giving you an intuition. This just now only it came to my mind that, okay, for example, if you can get rid of feedback if these spaces are so generalized well, and you know the mapping, you don't need a feedback.
Very, nice. Feedback is just
this is from
observation.
observation I'm trying to relate. Any learning model, they actually made this feedback, this RL. So technically, that's why supervised learning and RL is different. But the difference is due to the, like, the main difference in RL and supervised learning is the problem definition and the setup of, right. But now if you think of operator, now the neural operator is even a superset of all this, I'm saying, because by definition it has taken us from, so supervised learning, so far we have seen images, audios, or it's just discrete amount of
then we are back at AGI
data.
now.
What is that?
What is AGI? Again, wait, I'm so confused. You still need a supervised. Acha, nahi. Even in Banach space, you need the data set of the AGI in Banach space. Never mind.
These are my ideas. Like, all I'm saying is you can generalize RL very well if you know the mapping of one function space to the other function space. That's my claim.
Okay.
This is my claim.
No, agreed.
So I think, and that's because I think any be it you build a robot, you build a weather forecasting model that these were actually developed for building the weather forecasting model and everything. The game became so, like, it became more powerful because of generalizing it to a functional spaces. Rather than having a model, you're having an operator. That's the beauty. And since the world is again and again, this is the point that I'm highlighting, that you have equations, you have those crazy mathematical equations. Some has gradients, some has, those scalar field divergence, a lot of laws. We have electromagnetism, those 4 laws of electromagnetism.
Maxwell's laws.
Maxwell's law, yeah. So everything could be modeled by neural operator. This is my claim. Someone will do that paper and put it in neural. So I'm pretty sure someone will do that and put it
Yes,
on.
I see where you're going. But again, no free lunch is solved because even with
I
a neural
think
operator, if I want AGI, I need data set of AGI. So
Achha, you are into AGI, no matter what I see. Okay, you will never forget AGI. I hate this word anyway. Okay. So now
the
with
goal
this,
is that
what is that?
it's not like it'll ever be made, but the fact is that the very fact that you can try and you're always getting closer.
We are always
You-
getting closer. It's fine. It's fine. Every day we get closer. But with this
so much
discussion,
tool.
I think just check page 7. Just check page 7. You should be good with equation 2, 3, 4, and 5 now.
I am good with equation. Yes, I'm good with equation 2 very easily, good with equation 3 extremely easily. 4, which is minimization, is approximately 1 by n minimization. Like
again, expectation is just an average.
So why is it approximately equal to 1 by capital N, where
because of the discretization thing that is going on. You cannot get to the very close original. You will always approximate no matter what.
So this is a numerical method we did here?
Huh?
This is just a numerical analysis we did here, which is approximating
This
it,
is
right?
very much, yeah, just like last week I said, right? You go from one step to the other step, just like putting equal to, you're just having that approximation. Generally, expectation of something, expectation of a function. This is continuous. And think of that expectation of you're rolling a die and you kind of want to find what is the expected number of the
6.
I'm just saying, then you have to probably do the average divided by the number of, that will get you to this kind of notation, is my saying. So if you really try to find out this kind of thing, expectation in there is a probabilistic. These are like one way or the other, depending upon the wherever you are using, which literature you are using, you are kind of defining. That's the case.
Okay. I understand 1, 2, 3, 4 now. Sorry, 2, 3, 4. 5. Why is it called a super? Where what is?
You remember I gave you this notation? Now I'm reminding you what I said. You remember this kind of notation I gave? Oops, why is this? Where did it come from anyway? Did you remember this notation? I said that it is the least upper bound.
Greater than equal
Something
to.
greater than, yeah, inequality. Supremum is the least upper bound. I think, just let me check. Supremum means yeah, supremum is the least upper bound. So over here, all we are doing is we are kind of minimizing it, right? And I think we'll just let me read once. This where error is measured and founded. And then he considers. So they say that which is more standard error metric in the approximation theory literature. Just read there once that. See, we will also consider the setting where error is measured uniformly over a compact set of A. In particular, if K is a subset of A, we consider this is to be more standard error metric in approximation theory literature. That's the thing that they are kind of looking at. If you read it, you'll understand. So if you minimizing an error means what? I'll go down. Let's see. Okay. Take your time. I'll wait until you get it there. If you read and then I'll probably go there. So let
I'm
me know
reading.
whenever you are ready.
Okay. You are saying rather
So
than
now
equation
forget
3,
about this. Now let me try to explain you. Then again we will go and map equations in your head. Okay. Minimize for it. For example, remember this. We are trying to do this, right? And we are doing some theta estimation. And we are talking about equation number 5. Okay. So right. Oops. We have some notation like this going on, right? Minimize. I'm not yet there with supremum. I'm just with. We are trying to do this. We are trying to minimize this error, right?
yes.
Right. So when we minimize something, for example, cool. I see what happened, but anyway. So minimizing something means what? Let's say x squared is greater than equals to 0, no matter what. Right? That means the minimum value of x is 0. That's
-1 or 0, actually. Yeah, fine.
it
Greater
cannot
than
be
equal to,
minus
yeah,
1
put it.
ever. It cannot be minus 1 ever. It cannot be minus 1. It's always greater than equals to 0. Any squared quantity is greater than or equals to 0. This
Yeah.
is
So what is
what?
the
This is
what are you doing?
this
We are
is the
finding the minimum value of x here, right?
minimum upper bound. I'm trying to minimum upper, what I'm writing, upper bound. My spellings are bad in the minimum upper bound, whatever. But now this you can write like supremum of x square equals to 0. Same, right? Supremum. You have this kind of element. Or A is because we are having that A kind of input going in. But now you will be able to understand why supremum and why it's not a
But this
supremum.
will also be greater than equal to 0. It'll never be 0.
I am giving you this example.
No, no, I know. But I'm just saying, even in the bottom case,
They're
even in
defining
the
they're defining the minimization of this error to be equivalent statement of supremum is my
ah,
point.
yes,
Doesn't
yes,
need to
I
be
fully.
greater than 0 or not, but that's the claim I'm saying.
The best world in life in the world, Kagar. If I make the best model, then this will be greater. Do you get it? Like in reality, also we measure this also anytime for any operator or any model. This will be greater than equal to 0.
That though for in real world model, sometimes if you really want to build something for the first time, your error will be 20%.
Greater
0.2.
than equal. uh, so supremum of this is greater than equal to.
No, I understand your point too. Greater than equals to 0. Yeah, I can write this statement equivalently, no matter what.
Yes. So
It will
I'll just make a comment.
any machine learning model will never get to an like I'll never get an epsilon like minus 1.1. It's not
वो तो
possible.
कभी वो तो my machine learning algorithm is actually smarter than real world. That would mean that basically my machine learning algorithm would be
Yeah.
would
Technically,
be
that's error is negative. Means it's
uh,
so there are models which has outperformed humans, right? For example,
humans did
classification problem is redundant. Now humans will not do classification anymore because machine has achieved that.
technique. Yeah,
There
I
are
mean
we don't need to classify for this kind of problems. Machines are always great to do this classification no matter what.
that is also not bad question. I'm like, wait. Yes. If the function to approximate is a human and classification is the problem setting, then yes, this supremum will be not 0, -1 for those, like for that model. That supremum will be minus. Because it is better than the human. It is better than the human. So yes, -1. Anyhow, coming back to topic. Sorry for the distraction.
So
I understand that's equation 5.
so this is our debate no matter what. Whenever we seek to learn something, we debate. But the truth is, here is the truth. That is, I bet there will be neural operators, or could be 50 years from now, could be operator version something. It will be imagination version of neural operator will solve these physical laws in such a way, they will know it in such a way. Don't say
Doubtful.
this anyway.
No. I understand your claim. I see where you're going. Everything I'll doubt because of noise theory. क्या Claude क्या बोला था? Shannon? Who? Information
Information, that's back in 1948.
नहीं. Whose master's thesis was this? Dude.
Claude Shannon is the founder of who actually developed the concept of entropy back in 1940.
Entropy. But no, he also, the reason for entropy came from his SNR work, or signal to noise ratio work. So basically,
everything was generated for the communication. So information theory is like you are sending beat stream from the emitter to the receiver, and generally what happens, you kind of flip the digits, right? Flip the bits, essentially, not digits, the bits. So how do you want to quantify? How do you want to reduce the error from that?
Yes.
Notion, all this.
What the minimum? Yeah. So from the minimum, so essentially his work in SNR is what gives you the idea of like how much can you actually extract and leave the noise aside. So
yes,
based on that logic,
that's the whole
if you are
logic.
going to tell me that I will make some imaginary generalized universal operator to that maps from observable universe to non-observable universe, chalo maan liya.
Digital twin, we are making digital world. Digital twin we are trying to do, right?
I don't know.
Be
Let's say
it a
it maps from
reconstruction problem, be it making a Burger's equation work, be it holding thermodynamics somewhere. I'm just saying this.
I fully agree with you, but all I'm saying is, let's say that operator maps from observable universe to non-observable universe. Let's fully, completely, totally generalize it. Thanks to Shannon, we can say
the thing
there
is
will
that
be some error.
I know your goal. You want to have a minimum AGI. That's why you are saying that
No. I'm just saying that claim that you just made, that okay, as these operators generalize more, we will be able to, predict all physical laws. I would tell you that no, because of Shannon.
No, I can't agree, and we will not get into this debate today.
No, easily. So, वो side discussion. But I understand equation 5.
Silly to me. I don't have enough. I don't currently have enough time because I really want to go to section 2.3 and quickly.
Yeah, exactly. We will talk about that in actual when we
Shannon
meet.
thing we will have again. People come out of his office. Okay. We made so much of noise that anyway. Okay, now let's go to section 2, and I want to claim this now that we have had so far the spaces. So we were talking about these spaces. Now we will look how the spaces, because either way we are in a data-driven world, how we can actually have the spaces. That's why over here I'll probably ask you also to read, and I'll also reread. You will see that they have some sort of assumptions, okay? They say that AIs and the UIs are in general functions. That was clear from our discussion. And to work with them numerically, we assume that they have, okay. Another thing I want to specify, because this will come again and again if you read the paper, that is, let's see, function, well, I'll just write it out somewhere. Oh, sorry. Point-wise evaluation. So I think, let me ask you this question. Do you understand what point-wise evaluation is?
Quantizing something, quantizing a continuum, maybe.
You're right. You will always say in the other way. Point. Yes, point
I'm
one.
saying the other way. Quantizing a continuous space is what I
We are
will
always
read.
listen. Any
Ah,
function, yeah. You can think of it like that. Any function, if that is a function A, and if it is a, that's why we'll see all these small xl's are coming. So this
hmm.
A, if this is a function, you are kind of evaluating at xl, and that's why this xl, will see how this xl comes into the picture, and xl varies from L equals to 1 to L. So basically you are evaluating what is the value of the function at point x1, then at x2, and so up until xl. If you go and
Okay.
check the paper, because I want to make sure that you understand the paper too. So
I'm reading let D. See, I understand since AI and UI are general functions, they can only get pointwise evaluations. Now, the idea is assume D equals to D dash, where the input output both functions are real value, where DI
they
equals to
so this is basically they're assuming that this is to discretized space from the initial function to the output, or from the input function to the output function to be same. Does that make sense? That's why for simplicity, they say, they have also said it like for simplicity. It could be not equal. Most general case, they won't be equal.
I was just going to be like, dude, if this was there as an assumption, what's the point of this operator? Boom, pick. Like, do you get it? Like, what? If this assumption is true for everything, then it makes it kind of moot. Like, one of the strongest points of this paper is that I can go from any discretization to any discretization. If the input and output discretizations are same, then it makes the paper less strong. That's what I was going to say.
Say it again. Someone made noise here, but say it again.
Assume, okay.
Mhm.
Assume I have a plane where the quantization is 1 centimeter. Assume I have a plane where the quantization is 1 meter. Both are Euclidean space. Let's just first say. Okay. The idea is the strength of this operator is that I can map between making a circle in the 1 centimeter minimum space and 1 meter. But what you are telling me is that for assumption, let's assume 1 centimeter space quantization is equal to 1 meter space quantization. And then we'll understand the paper and then we'll do real world problems where they are not the same.
No,
So,
technically what they're trying to say in this manner is like, assume that 1 centimeter is equals to 1 meter or whatever by changing units. And remember, that's the beauty of Banach space. If you remember that old video that I showed where the circle is being equal to the square by the
yeah.
it's basically the same thing, right? It's basically the same thing. It's just
Okay.
the reason I think they have said, because what they want to hold here is they are also kind of discretizing the space into, over here L point discretization, it can mean any number of discretization. Now imagine if you go to figure 1, which is kind of finer and finer mesh refinement of that U or circle, whatever you can think of, the U shaped. It's basically those L's will keep on changing each time. And the more bigger you make the L, the more finer it gets. That's what L. So the picture in the right is more finer version. Right? Your L is basically increasing. You are making it super resolution kind of thing. Right?
Okay. No, so much more. This I understand. What the thing is telling me to assume is, imagine if the left side of the image and the right side of the image were the same thing.
No, I'm not saying that. Because over here, this is only at A space. This figure is at A space.
Okay.
You don't see how the A is being forward mapped to U space.
U.
I brought this figure up to give you an intuitive idea of how L can look like. How you can discretize the space is the whole goal of.
Okay.
This should be more clearer now, right? They have said this. For simplicity, now they are assuming that the L's in both. So the claim is why they have said this. And again, they have not clearly said, but my assumption is all they want to say, I'll write it here because I'll share this with you. is there is equal number of discretization levels in both input and output. That's why they have said it like that in functional spaces. And that is L. Now that's why I wrote it down. Does this make sense to you?
Yes.
Right? That's why they have made it. That's why they have said D is equal to T. It might look trivial to you, but it's just mathematical. I mean, there are many I have seen many setup like this where they have made this assumption just to make that the whole goal making D equals to D prime is just to claim that there are same number of discretization level. That's the takeaway.
You promised me Eiffel Tower. You gave me picture of Eiffel Tower. Okay.
Right? Okay, now what they're saying, now let's try. So they have 4 definitions going on. The first one is discrete refinement. And you will see these are they have you can just build it up yourself rather than looking at this, probably this union, the expressions of all this supremum and limits will confuse you. But intuitively, you will answer me how this math is building up, okay? And then discrete refinement, then they term something as discretization. The third thing they have defined is called discretized uniform risk. And the fourth one we have seen is the very important concept is this one, discretization invariant. And I mean, it might look easy to me. It's because I have seen so many invariant systems, for example, LTI, LSI, but I will not get into that because they are actually fundamentally different than these. This is something related to, again, sampling of the space essentially. Ultimately, it's a kind of sampling that's happening. You will agree to this, right? We are basically taking finer samples. You have that concept. See, they have defined it like this in this literature, but it's the same, something that you already know, and we will see that you know it. I'll prove that you know it. Okay. So discrete refinement. Now we have these assumptions. So, oops, why I'm not able to drag now? What? Sometimes I'm able to drag some. Okay, so I have to drag. In order to drag, I have to bring this. Okay, you can see it on your screen too, right? Because this view and that, my iPad view and my screen view are not equivalent. So now I think you will be able to see the entire whiteboard, right?
Yeah, God.
Okay. So we have these assumptions here that you are kind of chopping the space. Think that you're kind of chopping the space like this. Ti, and if you don't understand any of my writings, please let me know if I write anything illegible. So you're basically chopping the space. Does this make sense? Okay, now this you will not understand. This.
Can we back up a bit? But 1 second.
You're basically chopping that space T. and there are some L. The cardinality of points in the space is L. That means L number of samples from D.
Okay.
Right?
And the X is the smallest chop.
X is the point. You remember this functional space? Where did I draw the functional space? This. Yeah, this looks very weird on my computer too, and I didn't know this becomes so broad. But yeah, in my iPad I can see everything in a very notebook form.
No. It's
You can
fine. My
see, right?
monitor is also. I can see the entire whiteboard.
Yeah, and I can see whatever the place where I'm able to look
I
at.
know this is perfect. You are using Zoom correctly. I'm also using Zoom correctly. I can see the entire whiteboard, so I'm fine.
You
Plus
are
the following thing.
basically you are taking the points from where the function has to be evaluated. D is that space.
So it's a domain, no?
Domain, yeah, domain. Exactly, domain, right? But the function needs to be evaluated at some points. Your domain is real number. If you have a function like x squared plus 2, which is a in our case, now you have this x to be -1, and then a at x equals to -1 is -1 whole square plus 2. So x's are the points at which the function needs to be evaluated.
Okay.
Right? And D is equivalent to the set of real numbers. D is the domain. I'm just giving you an analogy so that you can have your calculus mapped to here and you don't have a trouble of reading the paper forward.
Okay. And now if I'm jumping ahead, they're basically saying make large L equals to infinity.
Huh? Yes, that is the discretization, discrete refinement. Refining means what? You are getting towards the more super resolution kind of thing.
Yeah. So basically L becomes infinity. I don't know how the domain is belonging. D1 is a subset of D2 is a subset of D. That part I do not understand, but I fully understand why discretizing it or basically quantumifying it
Now
or
I will
breaking
say
it
why
down.
it is subset. Okay. Now I will say why it is subset. Listen. So let's assume that D1 is this. In order to make it subset, that means, so oops, we need to have more finer. Let me change the color and let's bring this color. That means if D1 becomes a subset of this, that means there will be more points, and also these points will be in.
Acha, but okay, so it's not like there's a Venn diagram here. No.
It's still the way you can think of that. Yeah. You can think of that.
But materially, nahi. Matlab, let's say I take a room. The room is not being subdivided. All you're telling me as a subset is
The functional
D1 is
points, what you thought was function, I'm telling that these are the functional points where the function needs to be evaluated. So these are the gaps you have had. That's why it seemed difficult, but now it's becoming clear. So now I'll take more samples. Again, the samples from D2 will be there. In D3, there will be more
samples. So
more
D3 will
sample
be.
points from where the function needs to be evaluated.
I keep doing this, I'll reach D.
You will reach D, and D is that subset. So I guess you can
Superset, but okay.
Yes, superset. And that's why I'll just still write these equations down so that either way I'll share this so you can always
And the
back and
union of all of these points from all of these domains. Second part, which is y minus x less than equal to epsilon.
let me
That
do
part.
that. Wait, hold on. Let me still formally write this. So you have hold on. I don't want to mess up my write-ups because These chances are also for me to make notes. Hmm. So this is basically this. Cardinality means the number of points. And this L can be, L varies from 1 to, that's why they have said L belongs to N, right? Such that for any epsilon greater than 0, there exists a number L such that D is subset of union. And let me write, I'll try to say Y belongs to RD, Y minus X, difference is less than in norm of those 2 points is less than epsilon. It means that, and again, this is what I understood from this is any point this X. So Y and X's are the points from either a D or D1 or D2. For example, I'm considering D1 and D2 to be the subset, and that distance will be actually less than epsilon. It means very tiny difference. Infinitesimal difference, or technically you can think of null, the way I have shown the sampling. And it says
So,
that
okay.
D is union
Sure.
of all the points of this. D is
obvious.
union of all the point of such points. D is union of all such points. Does it make
Yes,
sense?
agreed. No, yes, you took the English statement and wrote it in math. The definition.
So that's why I drew that figure. That's
Yeah.
why you see subset and equals to. Subset and equals to became at this. See, this is how the beauty of math is, to express my words into these equations. That's why in the upper equation you have only subset, subset, subset. And this picture will justify how the union is actually working. That the picture that I drew in the left-hand corner, top left hand. And why this is subset? Because once you get all the points, you are actually reaching the ultimate D.
Full space.
Full space.
Everything.
And Y and X's are these sampled at different subset level.
Subset level.
Subset level means D1, D2. I mean D subset level, D1, D2, D3. Because think of this now.
Yes. Yes, I just ran that in my head. Yes.
You will never forget the way I'm explaining. That's the case.
Yes, it's impossible because I literally just saw that diagram again in my head. I'm like, Y and X
And
position
this
will be.
difference is epsilon. If it is close enough, and if it is just exactly the point, the epsilon is 0. Digest.
Yes. Nahin, so digest understood completely, because yes, there is. I don't have any doubt. Moving on.
So discretization refinement. Now it says that given a discrete refinement, now if L basically is your, now they have said, okay, this mathematically can converge to infinity. That's DL. L goes from 1 to infinity of domain D belongs to. Acha, RD, it's because it can be, again, I have not explained this RD. Again, in my understanding, these people have never brought these notations up in any of the talks, be it Camier, be it Zongi, be it Animas, be it Andrews. None of the authors have brought in their talks about the nitty-gritty of the dimension, space, and everything. But D can be RD. Okay, I'll clear this term RD also. In the picture that I drew, it has X1, Y1. But in a hyperspace, D, it is a D-dimensional. That's why RD. This RD.
Okay.
In this case,
So-
D equals to 2. The
So D
picture
means
that I-
dimensionality. Thank God. Okay, fine. All right. I thought that just meant real space. I did not know.
This R is real, but this real is D-dimensional.
It's not R square.
It's not R square exactly.
It's
Or
R.
in our three-dimensional reconstruction, we are in this space. For
So,
example, nerves are being characterized by in R3 space, but it is parameterized by R, G, B, theta, or the alpha is the volume density, but the input space is the positional and the. I'm just giving you the analogy from what analogy drove me to like explore the area. Theta and phi. This is A, this is U, but these are discretized and we can have it more because nerve is again a continuous representation. Gaussian flat is a discrete representation. Nerve has its own beauty. It's continuous, implicit.
okay.
Now, okay, this is clear to you what RD is. This is clear to you, right? So they have said that that's why discrete refinement DL goes from 1 to infinity of the domain RD because the real number is D-dimensional. Any member DL is, so basically now any member like this is called discretization of D. That's what they have said. Any DL, that's all it says. And also they have gone ahead and explained like, okay, think of this that there is another mapping going on because now you are evaluating the function at that discretization level. See, pointwise evaluation of the function. Now they have come the pointwise evaluation of a function because now you have to refer to this figure that I have drawn here. So this is basically mapping this RD because once you because we will be having functions also evaluated at functional points. This will be probably at Rn space. Now we have just we cannot go beyond any two-dimensional space for our discussion today. But imagine this picture. And that's why they have said pointwise evaluation of the function, and that brought the mapping of Rd to Rm, because the points in the D space, the D functional space were D-dimensional, and once you if you take those points and put it through the function, if you discretize them, that's what they have said that by Rm here. So that's the discretization is actually mentioned by the point itself, XL, and the functional value at that point. And that you can do for L equals to 1 to L. Each of them is termed as discretization. Now read that, you will understand. And they have defined A to be the function, which is R the T to Rm. And that's why I drew that function, see? And that's, they have also like, you can, while you are reading this, keep in mind the picture of the Mills refinement. That will complete the entire picture. Simple words. Well, that's the mathematical notation of that picture.
So
Whatever I went through.
why is this a cross product of that?
That's because cross product. Okay, note that this may be viewed as a vector of LD times. This is nothing but here. I think this is cross product, Cartesian product as per set. That will be clear, I think, because you are defining an operator. Any operator is being defined by the Cartesian product. That's the next line they have defined, I guess. if you parameterize, sorry, if you try to estimate the G, and we are still here now. I feel like that could be the, but I might be wrong here. I might be wrong here. This is not a cross product, this is a Cartesian product. And by Cartesian product, just Google and see. Let's say you have two set like this, A, B is like 3, 5, 6. Then the Cartesian product should be 1, 3, 1, 5, 1, 6. It's the functional evaluation, because that point and the functional evaluation will probably, where did they go? Just Google out the functional Cartesian product. You can, I might be wrong, but I don't remember. I think this is what Cartesian product stands for in set. Just check if I'm right with the basics.
All possible ordered pairs.
Yeah, so all possible pairs are the Cartesian products. So this is what it is, Cartesian.
So why is that space discretized by L and having the...
No, wait. Because now this RL, L is the number of discretized, there will be cardinality, right? So D is, so there will be L number of spaces, and they have made that to be cross product because they have said that this may be viewed as a vector. Now you have a vector. If you take them all, if you try to, because I said that there will be a 2 and 4th of function and its vector spaces. When I was introducing, because they have gone too much of 2 and 4th of everything. They have established a concept. They have also made it equivalent to Banach spaces. Now you think this to be in Banach spaces, then you certainly need to have this LD by RLM, and my bad, I have to, because this is, they said that this can be viewed as a vector, remember. The vector, for vector you will probably concatenate them all, right?
Okay, fine.
This makes sense, right? Because
I mean, for this to be understood better by me, I need to understand Banach spaces a little bit better. Because I understand this in Euclidean space 110%, or metric space if you want to call it. But just to see how it can be represented as a vector in Banach space, probably something I'll have to see later. However, see, the previous statement I anyways understand. That is, if there's a mapping between RD and RM, then the domain is a subset of that mapping. That I
either
understand.
way, I just want to bring it a note to you. You are frozen at the moment. I can't see you, so
What?
I can just hear you, but I do not know if you are frozen yourself. You are just frozen.
1 second. Has anything changed?
Yes.
Yes.
It's better.
So yes, I understand that these are subset of a mapping from RD to RM. Because it's a point, and then it leads to data set Excel and evaluation of Excel, where L equals to 1 up to L. You completely understand that English statement. Absolutely fine. And this is essentially what A might be or small a might be. So small a ko, it's defined as this thing. Fully understand what small a is. You are telling me also that small a can be viewed as a vector, which is RLD cross, or sorry, a product RLM. This part, if I have to understand, I think I really need to understand how Banach spaces have definitions written in them in gender. Because I understand, like in Euclidean space also, if I do,
Even if you
uh,
listen, even
no,
if
I
you
understand. Oh, is this how? If I say R square is defined by Rx cross Ry, is this how Euclidean space be defined as? The xy plane.
Cartesian product of all the points, yes.
Huh. Can I say the xy plane is Rx cross Ry?
Yes, typically you can say that. I think so.
That's what I meant. Banach mein how this statement happens, I don't know.
That's why for Euclidean, I keep on saying it's quite important, right? That's the
Yeah.
reason.
I understand. But no, I understand definition too. I will read a little bit more on Banach side and come back from there.
Okay, so now let's see what it meant by discretized uniform risk. In general, by risk, we mean that okay, I will introduce the main equation of neural operator because my iPad's charge is literally 7% now. I have to charge. I have to go.
Part 2.
Okay,
After part 1.
No, listen, what I intend to, I'll definitely finish definition 3 and definition 4 today. I'll introduce the neural operator expression, which is equation 6, and I will reiterate this in our next meeting. Okay. I will reiterate this in the next meeting, which is 2 weeks from now, which is next week. I won't be able to take this load. I will push back the neural operator meeting. Next week, I'll be busy with all this assignments and
interview.
Yeah. So we will come back and catch up with this the week after that, which is typically 22nd. And the agenda of 22nd is I will finish this neural operator. Then you will give me some update on practical stuff that you had been doing.
Yep.
Okay. Okay. So okay. This by risk. What do you mean by risk? By risk, we mean that it's a kind of error, right? Error between. Now, are you aware of that terminology? Because we are aware. I mean, the courses that I took, we define risk to be an error function. Are you aware of that?
I know error is just Euclidean distance between expected value minus what observed value.
Not only that, for example, let's say you are trying to do the let's say I give you a problem like this. You're trying to design an fire alarm. Okay. So you are trying to find the risk when the alarm will. These are classical pattern recognition. Even in human vision, we used to. Our professor, Dr. Pelz, used to give an example of, let's say there is a wrong person, and at the security check-in, you really need to figure out a person is carrying an arm or not. So these are the risks. So risk is how you can actually design a system where you can kind of minimize the error. From that point of view, this kind of risk came into the literature, and they have defined risk as to in either of the cases, you will be, let's say you want to define a Bayesian system, then you can introduce it as a Bayesian risk, which is nothing but some sort of error. Again, the human vision class, we have learned about this, and this is pretty true even in deep learning too. Like precision recall, F1 score, and all those things. True,
yes.
positive, false, negative, true, negative. Right?
Basic benchmarks, yes.
Yes, right. Those are the also they from that place. Even if you root it down, if you really look at the bottom of the funnel, it's always risk. They originate from the concept of risk calculation, which is nothing but an error calculation.
Okay, another new thing to learn today. Nice.
So now I will formally define define what discretized uniform risk is. Okay. And yeah, so let's see. So they're saying that A is the Banach space of Rm. We still know that this thing, but I'll write it down for ease. Oops. You can see my handwriting. I can see. I don't know again what you can see.
As I said, I can see the entire whiteboard. For me,
But can you understand my handwriting? If you see the entire whiteboard, I can understand that you can see the entire space, but my handwriting is probably very.
I think I know the confusion. Yes, I have an enormous monitor. I have a 34-inch monitor, ultra wide. I can see everything that I can physically see. It is big enough for me. For you, in a smaller monitor, that will look like those everything that you're seeing is small. For me, your handwriting is very big. So
Okay then. Okay. A is currently I have just zoomed in, so perhaps can be the reason. So anyway, A is Banach space, and we have R because we have Rm valued functions. Remember, now we have evaluated the function. Does that make sense? That's why we have Rm valued function from Rd. We don't have this anymore because those were just the points. Now you have evaluated the function, and that's why it's Rm valued function.
and now I have to actually zoom in. Rm value describe risk Banach space Rm value function. Okay.
You understand that, right? We are no more in Rd. We are in Rm space because you have evaluated the function A on Rd, right?
Mapping,
Yeah,
no.
on the domain Rd. So they have cleared it out. Now let G be the operator. We have just said it again and again throughout. And DL be the L point discretization of D. Actually, they're just defining this.
Again.
Yeah.
Oh
And
my.
anyway, the G hat is the approximation. So this is the
For a
original one.
97-page paper, any repetition, I swear, I am angry.
But then they have to define no matter what. Because this is the discretization thing.
And
Now
GCAP
that's why they
is-
have said the vector in the previous line, and you were asking this. So
GCAP is the vector that they're talking about.
GCAP is the operator. Now you will not
GCAP.
see an operator.
Wait. Let G be the operator that maps from A to U, DLB and Ha. So GCAP
This is
is
the
such
estimated
that
operator now. We are trying to now G hat is
cap. I'm sorry, I'm calling it cap hat. Yeah, sorry.
GCAP, same thing. What I'm doing, operator. This is the operator that you are having your algorithm to evaluate. Because the G hat will only be, or GCAP will only be evaluated by thetas. This is what your neural operator will approximate, and they're defining this to be this is the complete A space. Remember, this is still the A space. We are still mapping. This is the original one. This is to be figured out.
I was just going to ask, is RLD cross RLM, can it be substituted by big A? Or is it actually small a there?
Capital A, the whole space, right? I told you these are all the vectors. I showed you the Cartesian product of all the elements.
Yes. So this is still capital A. The reason I ask is, why is it G cap then?
Because you are actually, the whole goal of operator learning is what? We are trying to estimate G by using G cap. And we will be introducing thetas later on.
Okay. When did we change it from dagger to fine?
They have made dagger. Again, dagger is the G over here. This is G dagger. If you really
I know. See, this is G dagger, G theta then. Okay, that makes sense. I thought G cap, matlab, okay, maybe we are doing some magnitude division here to
No,
find the.
don't. They have defined each notation in every section. So you should reach out. And I will probably reach out to one of the authors because equation.
Can I rewrite the paper?
Go and ask Zangi. I have to reach out because I didn't quite get equation 8 because I know I have to reach out to the authors to understand equation 8 is pretty challenging. Anyway, let me define the risk anyway. So the
Yes.
risk is nothing but I have to erase this for a moment. Oops.
The supremo of G theta or G cap DL A given DL minus G of A. Same equation as above.
Yes, same equation as for last week. But
Ah.
what is the change? The change is addition of discretization.
Yes.
Previously, I spoke about the approximation. This has discretization in it.
Ma'am, I'm going to ask a very naive, dumb question.
Yeah.
In 2 weeks, did we just do
Discretization and operator. Wait.
That's what I'm saying. Did we just evaluate the function at that point of G bar, G cross and G
in
theta?
2 weeks, listen. In 2 weeks, we have actually seen the approximation problem last week. Today, we have just focused on discretization. And
of the same approximation problem.
Approximation and discretization is different. Just like digital and discrete are different. Because you have quantization on top of discretization. In this setup also, and that's why I hate CS people. Anyway. Sorry.
Continue.
I'm so sorry.
No, please, no. I want to hear the next because I'm going to ask a question about equation 5 and this equation very soon. But yes, do tell me what digital and discrete difference you're telling me.
Go ahead, because I have actually defined the risk.
Yes. So
this is discretized uniform risk. That's why discretization is oh my god, no, 5% charge anyway. Yeah, go
if
ahead.
I take equation 5, okay, and evaluate for every point at A, will I not get risk?
So in previous equation, I have not introduced the set of points where you have to evaluate the function. Do you get that?
Yes. Yes. Yes, in that kind of space, first you have to make the points, then you have to evaluate them. I am thinking Euclidean grain size, which is like points to obviously exist. They must be existing.
No points.
I guess.
So if you go to Andrew Stewart's talk, the key idea is design and then discretize. So we are designing and then discretizing. So the approach is different. Okay. Next is
You should hate CS people. Yes. No. Yes. Understandable.
Now,
okay.
Now, because I am surprised because in your CS department, the way pattern recognition is offered, we are taught in a very different way. We just do maths. We don't do coding the way you guys are taught pattern recognition anyway. Then talking about this discretization invariant. Now, when do you call it invariant? When you do not so I show you that sampling picture. Let's get back to the sampling picture so let's say I take the sample, orange sample and blue sample in such a way that the distance is 0 in between those 2 points. That means the points do not vary, right?
Epsilon is 0.
Epsilon is 0 and the subset of points at D1 or at an instance of D2, those points are literally the same. That is discretization invariant. That means when you are discretizing the D subspace into D1, D2, D2, D3, basically you are taking the same point. That's what they said, that now they're defining. Now read this statement, read this limit. I'll write this discretization invariance. Limit L tends to infinity. The risk of the operator that needs to be evaluated and the discrete hat that you have given. That's why they have written like this. That is also, see, they have added 2 dots because I feel like one added dot is for the L level, and that's why they have made it from GK to, or sorry, not GK, just I was correct initially, G. G to G hat. And I know you'll get confused, so I will wait.
I'm already confused.
Wait. Oops, no, that's bad.
Go back to the diagram.
Wait, let me write this. I bet my iPad will die. Anyway, okay, DL is the discretization level tends to 0. This is the risk means what? The error between 2 points. The error between 2 points, 2 entities. I have written it in a very bad manner, so give me a moment. I will write it again. DL. So they are kind of discretized for L levels. G cap is the discretized version of the operator that you will be learning with parameter theta. G is the approximated version that you already have had. And that limit will go to 0. Now, if I go to the function space, because if I go to the picture, and these are very hard to explain also. If you look at these 2 points, if you're now imagine that blue point, you start with some approximated space. And if I change the color of that blue points, you start with orange, red, pink, whatever, you're kind of discretizing the space. Imagine that blue, what is fixed at the beginning is your G space. And the more you do the subdivision of points by having orange, red, yellow, or pink, whatever colors, is your that discretization.
Levels of discretization.
Yeah, levels of discretization. Now that
Okay.
if you have those points being mapped onto the blue point, that is 0. So in that case, discretization is invariant. It means that whatever you started. Now this equation makes sense?
No, what you said makes sense. Now I'm going back to equation. 1 second.
It means that how much ever you do the discretization, if eventually all the points are at the same space, if all the points are very close, and eventually if they overlap, that is discretization invariance.
Fully understand what you said. I've understood the entire English statement of this. I'm reaching the point of any compact set K, which is a subspace of A, then risk at K for limit tends to infinity is equal to, we have to limit L tends to at limit L tends to infinity, R of K, this The risk is zero. Yes. So yes.
My analogy is clear now. Blue points
Yes.
and
Okay. Yes.
your
Yes.
ghanta understanding has given some meaning to
Yes.
your head.
Yes. Of course. Not some meaning. Yes. You're just repeating. Yes. Okay. Yes.
It may look like repetition, but approximation and discretization, that's the claim of the paper, that they have proved discretization invariant. So I couldn't escape this section. This is entirely a lecture. Discretization
No, no,
invariant
no.
is a lecture.
This is perfect. Yeah, I get it. This is the same thing where you said, no, you just can't say discretization can be ignored. No, you had the style of discretization matters. And again, approximation that you're calling also matters. However, why it matters is to prove that we'll be invariant across both. You have to say that you have to show it matters. No.
Say it, because I was writing, I didn't listen to you. Say it again.
To show a discretization invariant, you can't skip the step of discretization, nor can you skip the step of defining risk, if you want to call it, or RK.
Yeah, I cannot skip them. That's the
Yeah.
reason I'm going through every equation, dude, because the reason my NOR failed was because I think, I mean, I might have designed it in a wrong way. Could be. I mean, that's the reason. Not could be. That was the reason. But understanding these are very essential part if you really
Yeah.
want to go for implementation.
Yeah. No, but yes, I fully understand. To understand, and I'll tell you what I didn't, that I will go back home and read, which is basically A cross phi maps to U, right?
Yes.
That
Go ahead. Perfect.
A cross phi
Mhm.
maps to U.
Mhm.
That part, and G is the parameterized operator, and this is not G cross G cap. This is just new G, right? This is just new G, and or
Yes. They will be actually, this has its own realization. G is the original one, ground truth, which you don't know because it's hard to find. That's why you're using the mathematical, learning method, which will give you with some operator theta, but that's an approximated version. You need to have some sort of discretization one, discretized way of approximating it. So that's G cap. This phi is the representation, or you can have this numerical methods, however it used to be exist. They're efficient. They have been efficient so far, but if you use a learning method, it's cheaper and faster. These are more time consuming in a point of view, numerical methods.
okay, that is what you have been doing till now, anyway.
I've been just reading the theories, honestly. Theory is hard.
No.
Theory is quite
That
hard.
is what humans have been doing till now, anyway. The numerical methods.
Well, these are all statistical methods, but they don't involve learning.
Obviously,
What
statistics
so
does not have any.
humans are also making supervised learning and reinforcement learning.
What humans are doing, God knows at
Humans
this
are
point.
doing everything.
I
Stop. Anyway,
humans I give up on. Moving on.
Neural net, what we have seen, a normal layer of neural net is a linear multiplication and addition of biases, right? I will not go into too deep because I really am running out of time. It's 8:39 right now, and I have to wrap up. So yeah, my charge is 1%. The thing I want to write is, let's see if I can actually, let's see. This is the type C set. Should be fine. I think. Yeah, type C should work. Anyway, so G theta. Let me write and then I'll show you where these changes are happening. And you have to be patient because I'm sitting and writing this equation. I'll start from this end, as if I'm writing Urdu. But there is a reason. And this I felt why they didn't make it sigma 0, but I hated their mathematical notation for some reason. They are quite they're quite abrupt at defining their mathematical notation, in my opinion. This once again. So now I'm formally, for the first time, have written the expression of a neural operator.
G
Okay.
theta.
G theta. We will see how this parameterization will happen in the upcoming meetings and lectures. That I mean, anyway, I don't know if I really should call it a lecture, because there are many places where I also think that I don't know. But anyway, I hope I sound coherent and more clarified. Right. So what is the change that is really happening? See, we also have this, I'll make it W for consistency. We have a bias term, we have a linear operation weight term that is happening in the neural operator. The real change is happening with the kernel. And there is an P and Q that is, it starts with P, which is, I'll tell you, P is the lifting operator. And if you really use the neural operator toolbox, you will see this. You have to really play and plug and see what parameters you will use it, because this is something I did it last summer and I have just like made a disaster to my project. But anyway, so this is lifting operator. And what lifting means is like it lifts the input. So it lifts the input to a higher dimensional channel. That's why you will see that they are actually they are starting with some RDAs and they're mapping to RDV0, and DV0 is greater than DA. And this is more an art, you know, when you are designing a neural net or neural
it's an
operator
art.
it's an art. They have just made this heuristics possible. They have seen that this works and this works. That's the thing. So they have added this a lifting layer there. So that's the change from neural net to neural operator. So they have a lifting layer now. Okay, I'm selecting the selecting tool. Still, it doesn't allow me to. So we have a lifting operator here. Right. Then you have, I will introduce the Q first rather than the other thing. The Q is called projection. Projection operator, because it actually projects it back to the operator, like the original space. So Q essentially projects the representation, because you actually need to project it back, because you can never realize the representation, because we generally, humans, never understand whatever. For example, in a classification problem, definitely need to have the probability scores at the end. You have to have a representation that is human understandable no matter what. That's why you need to project back to the space. That's why you are doing a projection, because we are shooting the input to a very higher dimensional space.
Yeah.
And you have to project it back anyways. So that's the projection
But it's
operator.
the same. We pick DVT greater than DU, and hence it's the projection step performed by a fully local operator. So lifting, inverse of lifting will be projection.
Exactly. And in this
Okay.
case, dVT is greater than du, right? Now, okay, so now let's again get back to this equation that I wrote. So we see bias term equivalency. So P and Q's are the new addition. We see some sort of non-linearity, just like neural net. Weights are the weights, that's the linear multiplication. Biases are the biases. So now, and okay, this is, by the way, the term as the entire thing, they term as iterative kernel integration. Where iterative kernel integration. Iterative kernel technically is doing three operations here. One is, see, they have defined. One is local linear operator, which is this. A non-local kernel integrator, which is this.
Wait. Can you show again?
Biases.
Local linear operator, which is what?
Local
You have
linear
cursor on top of the screen.
the
I was zoomed in.
What is it? Say it again.
I was zoomed in. Your cursor went off screen. So WT
Oh,
minus 1 being the local operator, which is?
this is local linear operator is WT, wherever the linear multiplication, the weights, essentially.
Okay. And where is it? Which is what? Where have you written which is what? You're pointing at something, the screen went out.
This is, okay, I'll write it. I didn't write it here, but local linear operator. This is the kernel, the case. The integral kernel operator is the non-local. And bias function is bias function. This entire thing is doing the iterative kernel integration. If you look at page 9, read the statement 2, iterative kernel integration.
Yeah.
You get it, right? They're just making so much of noise here anyway.
But lifting and projection is not here. It is already pre-done to the input and output. That is our job.
Every parameter you have to figure out, no matter what, how you will play with the, so over here, the parameters, I'll tell you what, because I have literally played with it. You have to figure out the dimensions of this D's, essentially. DA's. If you go for an implementation point of view, you really need to play with the dimensions. What is the dimension you want to extend it to? What is the dimension? These are the parameter. And if I can, let me take a look of the neural operator. And based on, be it a graph neural operator, be it a Fourier neural operator, your parameters, you really need to figure out which one you need to tune in. Some things you can make it constant, and that's the game actually. But all I try to now, if I can, this is all what a neural operator is, which you have been looking forward to. Now take a look of figure. Let's try to look at a figure. If you go to figure 2, take a look of figure 2. Now everything will fall into place. Take a look at figure 2. Don't look at the different neural operator. Look at the very first picture, the very first integral. So each layer is actually, P and Q have been given by circles. And your iterative kernels are essentially this, whatever is like
A is
the
projected,
layers, layer 2, layer
and
3,
layers are
layer
there.
L. And then essentially this all will right?
Okay. Okay. And that's a DAG. What you're looking at is basically a DAG of a computer. Matlab, every NLP can be made into a little tree. That's a DAG of what the computations or operations would be. I can't hear you. You are saying, hold on. I know. Your iPad is dead. I still can't hear you. I'm reading your lips. I have no idea what you're saying. I can't hear you. You're muted. You are muted.
I'm trying to join in again. Hold on. So no, okay. All good?
Mm-hmm.
So all I was telling that now, if you look at the equation that I wrote, and if you look at the figure 2, you will be able to, you'll actually be able to relate, because you have P and Q, the layer 1, layer 2, layer L is essentially that iterative kernel integration. And under each that of block, whatever I wrote, forget about this integral and everything. I wrote the weights. I have shown that the summation of the weights, the integral kernel, and the biases being multiplied by a nonlinear activation, right?
Yes.
So this is actually the picture. And what they have claimed, so essentially I went until equation 6 so far, and what I will not explain in any of the meetings or any of the discussions that we will do in future, I'll never get into this Borel measure, and I'll never bring into this Nemetsky, and because they will make things even complex. But the whole idea from neural net to neural operator should be clear and sufficient with whatever I have just discussed.
No, no, no. See, this now, G theta definition, okay? This is very known. What you just did, this is a very known format and pattern. So this makes sense to me. It also makes sense as to how it can be written as that figure 2. So that's okay. But as for how they are saying that P and Q are interpreted through the extension of Nemetsky operators and they do not depend, then it's also written intuitively. Everything in paragraph 2, page 10,
Wait,
is just based on the user having a lot of or the reader having a lot of prerequisite knowledge.
you don't need that. That's my, you know, Banach spaces. Banach spaces is the functional space of all the function spaces. Forget about any other Lebesgue, Sobolev, or Besov, and Borel. In our RSN class, we have, like in the very first lecture, we were introduced to Borel. Like it had every functional space has its own set of norms that needs to be followed. That's it. Okay. And what they claim now is they have in this literature, they have made 3 kind of integral kernels, which is given by 7, 8, and 9. Okay. And you will see that it starts with a very common functional space, that is in equation 7, they have said that, okay, we have the Cartesian product of the d and the dt. T and T plus 1 is the next iterations technically. They have actually mentioned it to be two subsequent iterations, right? Iterations of the essentially the integral kernel, iterative integral kernel, the iterations. I believe so.
Okay.
Because no, look at the equation, right? If this is the entire iteration, your each functional block, each yellow boxes from figure 2 represents your part of the iterative integral kernel. And T's are nothing but it shows the timestamp at what your integral kernel is at.
Yes.
And that's why I said it's a two subsequent iterative steps.
Okay.
Right. So they have actually kind of, I would say that they have extended the space. See, they have so if you go to equation 8, and we will discuss this. And I honestly, I'll say that I don't have fair knowledge about why they have expanded the space, because see, they have did a Cartesian product of RDA, and I was sitting and reading and still thinking, why the heck was it? Why
Okay, chalo. Next week is equation 7, 8, 9, 10, 11. Next week.
Yeah. And I probably will reach out to one of the authors, like, why they have extended the space like that? Because in none of the talks they have gone at this level of detail. So I hope this was helpful to you.
No, this was very helpful because now I understand figure 2
Oh.
why. Because figure 2 is very figure 2 seems like someone took mishmash of this paper and then went like, hey, I copy pasted something into a typical neural network architecture DAG. Now figure